from really trying to get good semantic functors when we want to give some functorial semantics to these diagrams of network systems. So while John introduced decorated correlations to construct, cospans, thank you, to construct this category, I want to extend this framework and generalize it to decorated correlations. And in particular, the message, how are we doing? It's working on here. That's really weird. Is this synced to some?
Don't compose.
Yeah. Does this go and switch the slides? So I'm switching the slides on here, but not on the main screen. Okay, I think I'm. Don't know. We'll find out. Okay, now we can start again. So the message I want you to get after that pause is that all hypergraph categories are decorated correlation categories. So in the context of this conference, we saw David yesterday introduce hypergraph categories among other structures that come from operads of wiring diagrams, and in particular gave examples like the category of matrices or arrays, and also relations and maybe linear relations. John this morning introduced decorated cospans, and so what I want to do is sort of combine these two things. Then next, Dan will give a talk somewhat dual to this, talking about constructing hypergraph categories with the relations, and then we might see applications of this sort of stuff later on, say via Ross's talk. So let me remind you first what a hypergraph category is. And the slogan we want is that hypergraph categories model network compositionality. The picture we want is simply that morphisms in this category are hypergraphs. So slightly more formally, let me say that a hypergraph category is a symmetric monodal category in which each object is equipped with a special commutative Frobenius monode in a way coherent with a monodal product. So what does this mean? Well, as a category, we have these objects, and as a monodal category, we can put them side by side. If we have two collections of objects, we have things called morphisms, and in a symmetric monodal category, given two morphisms, we can compose them by sort of moving things along and connecting wires up, maybe switching, maybe permuting them a bit. In a hypergraph category, we're allowed this much more free notion of composition, where we're allowed to split wires, terminate wires, bend wires around, and connect sort of arbitrary or as many wires as we like together. So this sort of wiring structure is afforded by the special commutative Frobenius monoid on each object.
What's the coherent property?
The coherent property is essentially that if we have x and we have the multiplication of the Frobenius structure on x, and we have y and the Frobenius structure on y, then we can get the Frobenius structure on x times y by pairing them together. So the morphisms, there's no coherence with respect to the morphisms, which is interesting and perhaps a source of concern. But moving on. So now it seems customary to give a montage of network diagrams, but I'll skip past that and recall that John, in trying to formalize these things and formalizing these things and getting these steps towards a good general theory, formalized these as decorated cospan categories. And my claim in the previous slides is that these things should be formalized as hypergraph categories. So we would hope then, since John and I like to agree, that all these decorated cospan categories are in fact hypergraph categories. And that's true. So decorated cospans build hypergraph categories. In fact, this is due to sort of structure in the categories of cospans themselves. So if we recall, the setting is a category C with finite colimits, and we construct this category cospan C where the morphisms look like this. They're cospans. So every cospan category is a hypergraph category with a monodal product. I mean, John already went through the fact that they form a symmetric monodal category with this monodal product. more interestingly, now the Frobenius maps are given by the codiagonal map and the initial map on each object. So by properties of the coproduct, we always get a map from the coproduct of an object X with itself to X. And so we can get this Frobenius multiplication by using the codiagonal map, the co-multiplication by taking the opposite map, and similarly the unit and the co-unit are given by the initial map and its opposite. And this allows this more sort of hypergraph notion of wiring diagrams. So in every decorated cospan category, we get a notion of empty or undecorated cospan. And in fact, this gives an embedding of the category of cospans just in C into the category of decorated cospans. And then we can see the sort of hypergraph structure inherited along this embedding. Right. So decorated cospans build hypergraph categories. And this is great, especially syntactically. So if you recall, here's a decorated cospan category. If we have a decorated cospan, if we have another decorated cospan, we can stick them together, we can compose them, we can take monodal products. But if you notice, the decoration in the sense sort of grows and grows and grows. And eventually we put together big diagrams like this, which is great because we want to be able to describe these diagrams. But we don't want all our categories to be so free. In particular, we might want semantic situations where we start identifying different diagrams. So let me give you an example. If you consider this pair of decorated cospans or open circuits, they're just two open 1 ohm resistors, then their composite is, as this decorated cospan, is two 1 ohm resistors in parallel, in series. But in some sense, this is equivalent to a 2 ohm resistor. In the sense that they're equivalent is this: if we get these circuits and put them each in a black box, such that we're only allowed to probe the terminals by measuring electrical behavior on either side, so currents and potentials at these 2 points, then we could not tell these two circuits apart. They'll yield exactly the same measurements. And so we want to construct a semantic category in which these two morphisms are essentially the same thing, that this thing composes to this thing. And to do this, we need to use decorated correlations. So the key idea is that we can't see this center node here. We sort of don't even know it exists. And so we only want to decorate really the boundary of this cospan. So the stuff that lives can be said to live here and here. So let's see how that goes in practice. First, if this is just the pair of decorated cospans at the top of the previous slide, I'll just put them down there. And so let me remind you how we compose these as decorated cospans. First, we take the push out over y, and then we transfer the decoration up across this map from the coproduct, or the sort of disjoint sum of these two things, onto the new apex. And we arrive, and so this thing here is our composite decorated cospan. In this case, to move to decorated correlations, it sort of pays to run with this behavioral extensional idea that I was talking about earlier. So instead of decorating these cospans in this example with circuit diagrams, we're going to decorate them with measurements with the sets of possible behaviors or observations. So these are subsets of the space of potentials and the space of currents at these nodes. In fact, linear subspaces. And how you read one of these things is that this 1 ohm resistor corresponds to this space here, with this x being the potential over here, this y being the potential over here, and then then we have a constraint, right, coming from Ohm's law, which says that this 1 ohm thing here is the constant of proportionality between the potential difference in the current along this edge. So the current in at x will be x minus y, and the current in at y will be the negative of that, y minus x. So this is another way of describing these two 1 ohm resistors as two decorated cospans. Now, composing these again, we have a coherent way of pushing these decorations up onto this new apex. And the way is by identifying potentials. So the potential here, which I've written y, is equal to the potential here, which I've written y prime. So it's just y over here. But then we add the currents. So here, this is now 2y minus x plus z. OK, so that gives us the composite decorated cospans. But for a decorated correlation, again, we only care about what happens at the image of the new boundary. So we're going to factor our map into a surjection or an epimorphism onto the image, and then a monomorphism or injection into the codomain. And then we have a coherent way of transferring our decoration up onto this new apex, where we've said that, well, the potential here can be anything we like, so we'll just forget that y. But we don't want current leaking out in the center of our black box. So we're going to force this to be 0, so then 2y equals x plus z. And if we do some algebra, we get this subspace up here as our new decoration. Now, one observation so this is our new decorated correlation, and one observation you can make is that the constant of proportionality between the current and the potential difference is now 2. So this sort of corresponds in this picture to a 2 ohm resistor. Right, so let's recap that quickly. What happened was we had this decoration coming from our two decorated cospans. We transferred it up onto the pushout, and then we transferred again backwards along this injection onto the image of our boundary. So to introduce some notation for that, we write our composite cospan like this as f, and what we did was we factored it into an injection and a surjection, and then we transfer the decoration along this map here. So to construct our category of decorated correlations, we need a notion of transferring decorations forwards along a map in C and backwards along a map in M. To arrive at these factorizations, we need, in general, what's called a costable factorization system. And here, so in this example, C was the category of finite sets, and then this factorization system was the surjection-injection factorization system. So more generally, we write this for the category with morphisms, a morphism in C, then a backwards morphism in M. And now, to construct decorated cospans, we used a functor from C to set, because all we were interested in doing was pushing decorations along maps in C. But now we have this slightly more general category here, and a functor from C composed M of. And the main theorem then is this: in exactly the same way, we now get we always got a hypergraph category, but in particular we get a hypergraph category of decorated correlations here, where the objects are the objects of C, and the morphisms are decorated cospans subject to the constraint that these cospans are what we saw as jointly epic onto the image. So this is, in the circuit example, this was a joint surjection. But more generally, it's jointly lying in the first half of our factorization system. Right. So for functorial semantics, it's important we also get a hypergraph functor. And in the same sort of way as we did for decorated cospans, given these more general functors and a natural transformation between them, we can also get a hypergraph functor giving semantics from our between, say, a syntactic category, which could just be cospans if we use a trivial factorization system, to something like our linear relations, built as a hypergraph, built as a decorated correlation category. And then the main theorem I want to present today is that every hypergraph category is equivalent as a hypergraph category to something constructed in this way. In fact, we get an equivalence of categories once we allow for a notion of change of base, right? So we can change our category C, where these cospans live, and our factorization system. And we get a category of decorated correlations decorated correlation categories. And this is equivalent to the category of hypergraph categories. So to recap, the first claim was that we can use hypergraph categories whenever we want to model this sort of notion of composition. And then we saw that decorated cospans give hypergraph categories, but in sort of a free or initial way. And so to get at coarser notions of semantics, like this black box idea, we can use decorated correlations. But then the theorem is that this solution is general, and whenever we want to construct a hypergraph category, we can use this sort of technique. So, thanks.
I have a question. I know what a factorization system is. What is costable in this context?
Right.
Stable. It looks like costable.
So what this means is that the class M was stable or is stable under pushouts. So what this means again is that given, so say we have a map in M and then another map in C. Then if we take this push-out diagram, we get this map here will also be in M. And that's important for both composing correlations by taking push-outs and factorizations and making sure you still have a correlation, as well as making sure the decorations transfer nicely.
Hey, Brennan, can you comment on the relationship between hypergraph categories